Okay, so last section we're going to look at that has trig identities in it is section 7.5. Okay. Most of these identities, as I said, you're using calculus. We're going to see in 7.6 where you can use some of them to solve just basic equations. Right? So we solved a lot of trig equations graphically. And the way we did it is we put something in y1, put something in y2, and we look for an intersect. Well, some of those equations we don't have to graph. You can solve them using identities. Right? But it has to be set up just perfect so that you can do it. Most trig equations, if you just make one up, it's going to be very hard to solve it. Right? But if you set it up in special ways, it's doable. Okay, so we'll look at some special equations that you can solve tomorrow using some of the identities we learned today and some that we learned in 7.4. So, first thing is, let's look at those two things. One of them is sine of x with a plus 3 inside the argument, and then the other one has plus sine 3 on the end. It's almost like you tried to distribute the sign. So we're going to see, can you do that? Does that work? Well, when you add or subtract a number inside parentheses, what kind of transformation is it? Like how would a plus 3 move the graph of sine x if the plus 3 was on the inside?
It would horizontal shift to the left.
Yeah, this would be a movement 3 units to the left, right? How about when you add something on the end of a function? How does that move it? Up and down. So that would take the sine of 3, whatever that comes out to, and move it up. So just looking at it from a transformation perspective, those aren't the same. You can't use the distributive property with a function. If it was a number on the outside, yes, you can. Like if it was a 2, you could write 2x plus 6. But a function, no. Can't distribute a function. So, what we're going to look at is 6 different identities for sum and difference. Right? There's an identity for when you have a sum here and a difference for sine. Then there's one when you have cosine. Sum and then a cosine with a difference. And then there's one for tangent with a sum and tangent with a difference. The sine and cosine ones aren't bad. The hardest thing about them is they're all very similar, so it can be tough to remember which one is which. The tangent one, I usually never remember that one. So if I need to use it, I always have to look it up. All right. So I'm going to start you guys off with this formula. Now, you can prove it. The proof to go through this, it's a little difficult, and it probably takes about between 10 and 15 minutes to prove this formula. So for our purpose, that's just a lot of time to kind of show this one formula. But once you have this one, then the other formulas are very easy to get from this one. Right? So we're just going to start with this one. Okay, but the proof, it is in your book on page 409. And this is called the cosine difference formula. And I mentioned earlier that you can use these to solve equations. You can also use this to figure out something numerical. So in a minute, you guys are going to be able to figure out something like that. We usually only work with angles that are multiples of 30 and 45. When I ask you for exact answers, that's what we usually do. Well, now you're going to be able to extend that a little bit. You're going to be able to work with anything that's a multiple of 15. And this formula, I'll show you how you do it. So think of alpha as the first and beta as the second. So if you have the cosine of a difference, it's cosine first, cosine second, plus sine first, sine second. Okay? Whatever you have here, these two things are usually numbers if you're going to do something numerical. Okay? And you could graph that. You could try it and see that what's on the left and what's on the right, especially if you just pick a number for one of them, because you can't graph two variables. But let alpha be 10, and let beta be x. Plug what's on the left into y1, put what's on the right in y2, and you'd see they're the same. Or pick any number you want for alpha. 15, it doesn't matter. Okay? But that's called the cosine difference formula. So we are going to hold off on the proof, but it involves looking at two diagrams, which we're not going to do. Okay, what we are going to do is use the formula to figure out the exact value of that. Now, this, if I use the calculator, put it in degrees, and press cosine 15, that's not the exact value. That's a decimal. So I don't want that. And there's no way to convert that to a fraction because you can try. But the fraction is going to have square roots. Okay? So we're not going to be able to use the calculator to change it to a fraction. So the way you can figure out cosine of 15 is you're going to use this formula, and you have to pick a number for this and pick a number for that. So when you subtract them, the answer comes out to 15. But you can't pick any two numbers here. Like you could say, well, could I do 20 and 5? Yes, but then the problem is going to be when you try to fill in 20 for alpha over here, we don't know how to take the cosine of 20. That's not an angle we normally work with. Okay? What kind of angles do we normally work with? Multiples of 45 and 30. So the two numbers that you pick here have to be multiples of 45 and 30. Okay? So numbers like 30, 60, 90, 120, 150, those are good numbers to pick because we know how to work with them. And numbers like 135, 225, 315, those are multiples of 45. So, anybody think how I can write 15 as a difference?
You have to do 45 minus 30.
So we're going to do 45 minus 30. So now, in this problem, alpha is 45 and beta is 30. So this whole problem is going to turn into taking sines and cosines of 30s and 45s. So that's where we get fractions like root 2 over 2, root 3 over 2, things like that. All right. So let's write it out using our formula. Let's see if we can go like this. So it's cosine first, cosine second. Cosine of the first, cosine of the second, plus sine of the first, sine of the second. Sine 45, sine 30. Now, this is the part where it helps if we have all these values memorized. Okay? If you don't, you can plug it in on a calculator, you'll get a decimal, but then you have to recognize that decimal as either the square root of 3 over 2, square root of 2 over 2. Those are pretty much the only ones that come up when you're dealing with sines and cosines of 30s and 45s. When we get to the tangent, square root of 3 can come up as well. Square root of 3 over 3. That's another special one. Right, so all the numbers you're going to get here are numbers we looked at when we did unit circle. Right, so let's look at the cosine of 45. Before I type, does anyone remember what that is? The fraction? So if you type it in, hopefully that jogs your memory. It's 0.707. Anyone remember how you can write that as a fraction, but it has a square root in it? It's one of the ones I said earlier. Square root of 2 over 2? Yeah. That's the square root of 2 over 2. Why? Well, that's what we did when we did unit circle trick. Okay, we spent a day or two on drawing 30, 60, 90, and 45, 45, 90. So that's one you want to remember. Okay, so when you see 0.707, that's the square root of 2 over 2. Times, right, let's do cosine 30. 0.866. Anybody remember what that one is? So that's part of the 30, 60, 90 right triangle. The 30, 60, 90 doesn't involve the square root of 2. It involves something with a square root of 3. Yep. Square root of 3 over 2? That's square root of 3 over 2. And there's not that many you have to recognize when you do sine and cosine. That's pretty much it. Okay. Tangent, yeah, there's more. But that's it for sine and cosine. So 0.866 is root 3 over 2 plus. Now we need the sine of 45. Okay, that should look familiar. What's the sine of 45? It's the same as the cosine of 45. So square root of 2 over 2 times, and the sine of 30, that is 1/2. So if you don't remember it, you can check it, but we'll just write it as 1/2. Okay. So now we simplify what we have there, and that's our final answer. So the fractions on the left side of the plus sign, we're just going to multiply straight across the top. Then we'll do the same on the right. Derek, what's the square root of 2 times the square root of 3? Like if you were to combine them. Well, do you remember like how you would simplify something like that? Yeah.
Would you take it and like make it like 3 and 4?
Right.
And then,
You could go like, so you can split that up into 2 fractions. Well, this is the reverse. You're not splitting it into 2 fractions. You're taking the 2 roots that are separate and putting them together. So it's the square root of 6. Over, what's my denominator? 4. Right. When you multiply denominators, you don't have a common denominator. That's when you add. Okay. How about over here? What's that fraction going to be? Square root of 2 over 4. And now to add those fractions together, what do we need to make sure we have? Which we already do, so we can just put it all together like this. And that's the exact answer for the cosine of 15. Let's check. Cosine of 15 is about 0.9659. Let's type that in. The square root of 6 plus square root of 2. That's just the top. Divide by 4. 0.9659. Now, honestly, in calculus, you're probably not going to do this with numbers. Most of this formula is done when you have letters. So it's a little bit different. Or maybe one letter and one number. Okay, I might show you guys one of those in a little bit. But I'll give you guys some numerical ones like that on the test just to practice. Questions on that? Okay. Let's look at this one. So that's an identity they want you to verify. Last week from section 7.4, you couldn't have done that. Okay. But look at what's on the left. That's the same pattern we just had before. Cosine of a difference. So we just have to remember the formula. It's cosine, cosine, plus sine, sine. Cosine, cosine, plus sine, sine. And that's like my alpha, and that's like my beta. Okay, so what we're going to do is we always work with the side that's more complicated, which in this case is the left. Leave the right-hand side alone. And when we're done working with the left, hopefully we get what's on the right. Okay, so it's cosine, cosine, and then was it a plus or a minus? Plus sine, sine. Now fill in all your arguments. So Skylar, what's going to go in the first parenthesis? 5 over 2. Peregrine, the second parenthesis? Theta. Now, in the other part, sine of, say on my first parenthesis? Theta. Let's go back and let's just double check it. So, the order that they usually do it is first, second, first, second. Technically, these are commutative, so you could do sine beta, sine alpha, but I'm just going to stick with the same order. Right. just to make sure we match the formula. So we're going to do pi over 2 and theta. Now, because these are sines and cosines of 90, we shouldn't even have to plug it in. Just think of the picture in your head. That's the graph of sine. Here's the graph of cosine. And the quarter points here, here, there, and like this. So, what's the cosine of pi over 2? 0. Okay. So that's going to be 0 times cosine plus, what's the sine of pi over 2? 1. Sine is 1 times sine. Let's do it like this. 0 times anything, what happens there? So that whole part cancels out, and now you're left with 1 times sine, which is what? Sine. That's exactly what you wanted. So by using the cosine difference formula on the left, we turned it into what was on the right. You'll probably have 1 or 2 like that on the test. Could be a cosine sum here, which I haven't shown you yet. Could be a sine difference or a sine sum. Okay. Or a tangent difference or a tangent sum. There's really 6 of them. Questions on that? Okay. So, let's see if we can figure out the cosine sum formula. As long as you know the cosine difference one, this one's very easy to figure out. So, a couple things that are going to come up here that we have to remember. If you take the cosine of a negative angle, or take the cosine without the negative, what's the difference in the two answers? What?
There isn't one.
There isn't one. And that's true for any angle. And that has to do with, because when you graph cosine, it's symmetric over the y-axis. It has a symmetry to it. That's why these answers come out the same. Now, sine, a little bit different, okay? With cosine, whether you put the negative in or you don't put the negative in front of the angle, it doesn't matter. Let's try it with sine. So let's do sine of negative 35 and sine of positive 35. Did those answers come out the same? No. What's the difference? Yeah. So with sine, if you have a negative with the angle, you can't get rid of it, but what you can do is you can just move it to the front. And the sine of negative 35 is the same as the negative sine of positive 35. Okay? So with cosine, you can get rid of the negative. With sine, you're allowed to put it in front. And this has specifically to do with what we call even and odd functions. We don't really study too much about that, but that's what it has to do with. And I just showed it to you for 35, but if you could actually graph this on your calculator, put what's on the left in y1, put what's on the right in y2. They would look exactly the same. Okay, so keep those two things in mind. So we have a cosine sum. The only formula we know right now is what? Cosine difference. So then we're going to have to write that somehow as a cosine difference. If you can figure out how to write that sum as a difference, then we can use the formula we already know, figure out what it is, and then we'll have it, and we won't have to figure it out again. So how could you write what's inside the parentheses as a difference? As what? Yeah?
Would be A minus negative beta.
Yeah, alpha minus negative beta. Alpha minus negative beta. Now you have it as a difference. That's the first thing. That's the second thing. That's the 1 and the 2 that we're going to fill in those two spots right there. What comes before the minus sign is the 1. What comes after the minus sign, I'm calling that 2. So, what's before the minus sign? Alpha. What's after the minus sign? Negative beta. Do it out and see what happens. Right. So, Vinny, when I want to write out the cosine difference, what's the first thing I put?
You put cosine of
Yep.
and cosine of, in this case, negative.
Yep. Right, so let's start with that. Cosine alpha times cosine negative beta. We'll come back to that negative beta in a second. Plus
Sine
sine
of
of alpha. Yep.
and a sine of negative.
Sine negative beta. Okay. So in the first term, cosine alpha, cosine negative beta, what can I do to simplify that a little bit?
Invert to cosine.
Right. The negative in front of the beta does not make a difference because I didn't prove it to you, but I showed it to you with an example. So we can just write cosine alpha, cosine beta. Now, what about the negative? I can't do anything with sine alpha, but what about sine negative beta? I can put a negative in front, like this. It's really like multiplying by -1. That's what the negative on the beta does. So let's just put it in front. So sine alpha, sine beta. That is your cosine sum formula. Very, very, very close to cosine difference. What's the only thing that's changed between the two formulas? The sign. That's it right here. If you make that a minus, it's the formula we have now. If you make it a plus, it's the formula you had before. Okay? So with the cosine sum and difference, what you put right there is the opposite of what you have right there. The cosine sum formula has a minus in it. The cosine difference formula has a plus in it. So it starts to get a little tricky to remember. Yeah, just a second. Okay. So, sorry, I forgot to put that there. So what we're going to do is now we're going to find the trig value of another function that's a multiple of 15, but this time we're going to do 75. And I would like to try it as a sum. Pretty much anything you can do as a sum, you can do as a difference. So there's two ways to do this problem. But let's try it as a sum. So you have to pick two numbers that add to give you 75, and they have to be numbers that are multiples of 30 and 45. Yeah.
45 and 30.
Yeah. So it's pretty much as easy as you could get. 45, 30. And now it's just a matter of plugging in 45 and 30 everywhere you had an alpha and a beta. Right, so Kayla, what's the first thing that I'm going to put for my cosine sum? Yep, to do out what's on the right. Cosine 45. Cosine 30. This is a sum, 45 plus 30. So what should I put here? Minus. So with the cosine ones, it's always the opposite. When we do the sine ones, you're going to see it's always the same. So now minus, and then what would you put after it? Sine. Yep. Sine 45? Sine 30. Yep. The other thing, too, with the cosine formulas I gave you, the two cosines are always together, the two sines are always together. When you do the sine sum and difference, it's always one of each. It's like a cosine sine, cosine sine. So it's the pattern is switched up a little bit. All right, let's go through, see if we can remember these. What was the cosine of 45? Square root of 2 over 2. How about the cosine of 30? Square root of 3 over 2. The sine of 45? Square root of 2 over 2. And the sine of 30 is 1/2. Okay, so I'm just going to put it all together in one step. Denominator for everything is going to be what?
4.
Final answer is going to be 4. And what are you going to have in the top?
Square root of 6 minus square root.
And that's the exact answer for the cosine of 75. Done as a sum. Now, anyone, I'm not going to go through the whole thing, but anyone think they could tell me how to write 75 as a difference?
135 minus 60.
135 minus 60. Let's see, it looks good. 135 is a multiple of 45, and 60 is a multiple of 30. That would work perfect. So any formula, anytime I ask you to find a trig function that's a multiple of 15, some of you might see it as a sum. I personally would see this quicker. But if you didn't see how to do it as a sum, you could also do it as a difference. And you'll get the same answer if we were to go through the whole thing.
So you have the option to do either one.
So any questions on how we got that, or how we, I mean, I don't know how to tell you to figure out it's 135 minus 60. I mean, you just have to, there's only so many numbers to play with that are multiples of 45 and 30, and you just have to try to figure out which two you need. Okay. You know, if you're trying to get a number that ends in a 5, you've got to have subtraction with a number that ends in a 5 somewhere. You can't have two numbers that end in a 0, subtract them, and get something that ends in a 5. All right, so let's look at the sine sum formula. This is an identity that's kind of reminding us that sine and cosine are phase shifts of each other. I know it's written a little different, but that's basically what they are. If you take the graph of cosine and shift it 90 degrees to the, let me think about it for a second. 90 degrees to the that's sine. So actually it's easier for me to think about it as sine. If you take sine and shift it 90 degrees to the left, you get cosine. So if you take cosine and shift it 90 degrees to the right, you get sine. Right? So sine and cosine are just phase shifts of each other. So using that, we can figure out this. If you didn't know this, it would make it a little tricky to figure out. Okay, so to figure this out, it's gonna have to boil down to one of the formulas we already have. We're either gonna turn this into a cosine difference, or we're gonna turn it into a cosine sum. Okay. So we're going to turn it into a difference, because I'm giving you a way that if you have the sine of, let's call it square, it's equal to cosine pi over 2 minus square, whatever's in the square. Okay. So, anyone think they could tell me what I could put inside there using the identity that's above it.
Cosine of pi over 2 minus alpha plus beta.
Doesn't matter what's inside that square. If you take the cosine of pi over 2 minus whatever's inside there, that's what the identity is here. So here you had theta, there I put theta. Here alpha plus beta, here alpha plus beta. Okay. Now, what could I do with that minus sign in front of the parentheses? Distribute it. So let's distribute it. And now we have that. Okay, so we're going to look at this as a difference, and I'm going to write it like this. Cosine pi over 2 minus alpha. That's going to be the first thing. Minus beta. That's going to be my second thing. So if you're trying to like think about, well, what's the first and what's the second here? That's the first. That's the second. So now we're going to look at our cosine of a difference. We're going to fill what's inside those red brackets everywhere we had a 1. And we're going to put what's inside that bracket everywhere we had a 2. And see what happens. Let's write, before we try to do it, let's just write out the whole formula. For the cosine of a difference, what do we put for the operation? Addition or subtraction? Addition. It's always the opposite. Are the cosines together on each side and the sines together, or are they both mixed? Let's go back and look. The cosine, they're together on one side. Sine, always together on the other. I know this is a sum, but if it was a difference, it would be the same thing. Okay, so let's put cosine, and then sine. Okay, what's going to go in my first argument? Pi over 2 minus alpha. So it's the cosine of pi over 2 minus something. The cosine of pi over 2 minus something is equal to something. So we can simplify that in a second. What's going to go in my second one? Beta. What's going to go in the third set of parentheses? Yep. Now, I didn't quite talk about that one, but I think you'll be able to figure out what that is in a second. And what about the fourth set? Beta. Now, let's look at the first one. You're not going to be able to do anything with cosine beta and sine beta. Those are as simple as they get. But the other two you can. Cosine of pi over 2 minus alpha. Cosine of pi over 2 minus alpha is equal to what? Sine. What's our letter we're using? Alpha. So anytime you take the cosine of pi over 2 minus something, the answer is just sine of your something. Cosine beta plus. Now, this is sine pi over 2 minus alpha. If cosine pi over 2 minus alpha turns into sine, what do you think sine pi over 2 minus alpha turns into? Turns into cosine. And that is the formula for the sine, what did we say? Sine of a sum. It's sine of the first, cosine of the second, plus cosine of the first, sine of the second. Now I get all mixed up which one's which. A couple things you can try to remember is when you have sine, the operation here matches the operation here. With cosine, it didn't happen. It was the opposite. With cosine, they were grouped on the left and they were grouped on the right. The trig function stayed separate. When you have the sine sum or difference, which I'll show you in a second, they're mixed. You have a sine, cosine, cosine, sine, okay, on each side. Now, some people might write it as like sine beta first and then cosine alpha second. That's fine. I just wanted to keep it alpha, beta, alpha, beta. I just like to keep that part the same. Okay, so that's your sine sum identity. Okay, so based on that, without having to go through, I mean, we could go through it, but what do you think the sign difference is? What is that?
You just subtract.
Yeah, just subtract, but it's all the same. Okay? It's still sine, cosine, cosine, sine, alpha, beta, in that order, but just change the plus to a minus. So the minus here matches the minus there. And what that would allow you to do now is I could ask you guys to do something like find the sine of 15 or find the sine of 75, just like we did cosine 15 and cosine 75. It would be very, very, very similar. So rather than actually go through those, I just want to see if you can figure out how to write a number as a sum or difference. Okay? I'll leave actually getting the root 3 over 2s, root 2 over 2s, and all that stuff to you. Let's say I wanted to find sine of 105. Now, I know it's doable because that's a multiple of 15. That's 15 times 7. So how can you write 105?
35 minus 30.
You could do it as 135 minus 30. Yep. To me, that's the hardest part, just trying to think of the two numbers. Now from here, I just fill them all into the sign difference. Anyone think how to do that as a sum? Because if you can do it as a difference, you can always do it as a sum. And I don't mean like 135 minus 30. Of course, that's a sum, but it's not really. Yeah.
45.
Yep. 45 plus 60. How about if I said, let's just pick, let's do 15 times 11. That's too big. I don't do that. Let's do 15 times. That's an easy one. All right, let's do 165. What I'm trying to do is find ones that aren't multiples of 30 or 60, because you already know that's not. But it is a multiple of 15. So how could you write 165? That's very similar to something we already have, yeah?
45 plus 1.
Okay, sine of 45 plus 120. Yep, not what I was thinking. I was thinking 135 plus 30. That would also work. How about as a difference? Sorry, messed that up. But 165.
And 210 minus
210 minus 45. Yep. Sine 210 minus 45. questions on it? Okay, now let's say that I asked you to do tangent of 15. I haven't given you the tangent sum and difference yet, but technically you could figure it out. How could you get the tangent of 15? Using something we learned last time. Yeah?
You just sine of 15 over cosine.
Yeah, awfully long way to do it, but you could. You could do the sine of 15, get that answer. Bless you. Cosine of 15, get that answer, and then divide them. Okay, so you'd end up with a fraction in the top, fraction in the bottom, so you'd multiply by the reciprocal. You could. Or, there's this formula. Now, I'm not as concerned about the tangent. Honestly, I don't really do a lot with it. Maybe one problem on the homework for the test. Sine and cosine is more important. Okay. And honestly, if I ever had to figure out the tangent of 15, I would just do it the way I showed you. I would do sine, because I think I can kind of figure that one out. This one's kind of complicated to remember. I would just do sine and cosine. Right, so that's tangent of a sum and tangent of a difference. It has the same pattern every formula that we've done today has. If you change this plus to a minus, change all the pluses and minuses to their opposite. That's like what we did with the cosine formula. It's the opposite. Not saying you'll never use that in calc, maybe you will. But as far as problems that I give you, even stuff we do tomorrow, I'm not going to use these. I think there is one question in the homework. Okay, so any questions on that whole group? Those are called sum and difference identities. For sine, cosine, and tangent. Okay, definitely the I think the hardest ones that we look at. Let's look at that. Without me even explaining anything, can someone tell me why these two are different? And I kind of gave you a hint when we did the first problem today. The first thing I put on the board, you could use the same reasoning here.
You're trying to change it from a horizontal stretch to a vertical stretch.
Yeah, this one on the right is a vertical stretch by a factor of 2. That's a vertical stretch by a factor of a half. That's not equivalent. I'm not saying horizontal. Okay, one of them's horizontal, one of them's vertical. They're not even close to the same thing. So, problem we went into in calculus, and even some of the stuff we're going to do in 7.6, you don't want to have a number with the letter. That makes it hard. You want just a letter here, okay, like an X. So there is a way to get rid of the number in front. And actually, I'm not going to do it as a verify. I'm not going to show you the right-hand side yet. We're just going to simplify the left and see if you can figure out what's on the right. This is called a double angle identity. What it does is it takes an angle that has a number that's a 2 in front of it, and it gets rid of having the 2. So it's a way to get rid of the 2. So just leave a little space here, and you can fill that part in after. But let's see if we can figure out the left-hand side first. How could you write sine of 2 theta, specifically the 2 theta part, differently? Think of like arithmetic you could do, and the answer would be 2 theta when you simplify it. How could you get 2 theta as an answer to some kind of arithmetic problem? Theta plus theta. So this left-hand side, you could write it like that. Sine of theta plus theta. Now, what is this? That's the sine sum identity. Let's see if we can kind of remember what it is and write it out, and that'll tell us the answer to what this equals. Okay? So we just wrote 2 theta is theta plus theta. Okay, I know that it has a plus in it because with the sine identities, plus matches the plus. Okay. What's the first trig function? So then it's a sine, cosine, cosine, sine, right? And we go right in order. First, second, first, second. What's my first thing that I'm adding? Theta. Second thing I'm adding? Theta. 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 So I have sine times cosine plus cosine times sine. Is there a difference between sine times cosine and cosine times sine? Well, like 2 times 3, 3 times 2. So this is sine cosine. This is sine cosine. What do you get when you add a sine cosine plus another sine cosine? That's multiplying. What do you get?
2 sine.
So like what would you get if you had xy plus xy? 2 of the xy's. So sine cosine plus cosine sine?
So it'd be 2 sine.
2 sine cosine. And that one's very easy to identify by using the sine sum identity. So what that did is it got this 2 out of here. Now you just have a theta and a theta. Okay, so that's our double angle identity for sine, how you get rid of the 2. Okay, there's one for cosine. Actually, there's a couple for cosine. And I think there's just one for tangent. Does anyone remember a Pythagorean identity, something squared plus something squared equals 1?
Sine squared plus cosine squared.
Yes. That's not what I'm going to use here, but if you remember this, that is how they get the different versions of the cosine 2 theta. That's the first version. Okay. We're not going to go through a proof on this one. Right? Cosine 2 theta is cosine squared minus sine squared. Totally different than sine 2 theta. Now, one thing you could do is, let's go like this. Cosine squared equals what based on our trig identity? Yep. Now, if you take that and fill it in there, you would have 1 minus sine squared minus sine squared. What's a minus sine squared minus sine squared? That's where that version comes from. So it's not really different. It's just plugging in the Pythagorean identity. And you could also do it the other way by plugging in for the sine squared instead. So depending on which one you substitute for using your Pythagorean, you can get these other 2 versions. Which one do you use in a problem? It depends. Chances are if you're doing a problem and there's other stuff in it that has sine, I'm probably going to stick with using the middle one. If the problem I'm doing has cosines on the other side of this equation, I would probably stick with cosine. Okay? Because the less trig functions I have in the problem, the better. I don't really like the top one as much because it takes what was just one trig function before and now introduces 2 of them. That complicates it a little. But it's a good starting point to figure out the other 2. So that's why we do it. And again, the tangent of a double angle, we won't be using it as much. My main reason for giving you that one is so if you do take calculus next year and you forget identities and you still have your pre-cal notebook, you're going to have every identity that you would need. Even if we don't use it a lot, you'll at least have it so you can look it up. Okay. So those are all called double angle identities. And that's the fifth main group of identities we've learned. Today we've done sum and difference in this one, and then we did 3 other groups in section 7.4. Okay, so they want us to write that basically without any tubes inside the argument. Why would we do that? We're getting ready to solve an equation. Okay, there's no equal sign here, so it's not like you're going to have to solve it. We're just getting ready for what will happen tomorrow, where the first step is going to be get rid of that tube. Okay, how about the first term? 2 cosine x. It's what? Is there a 2 though in front of the x as it is? No, so that's okay. If they said to rewrite it in terms of cosines, this one already is. It's 2 times one of the things they told me I'm allowed to use. 2 times cosine. So that's okay. The second part is not. And as far as double angle identities, the sine one is usually the only one that I remember. I always mix up the cosine one and the tangent, I never remember it. What is sine 2x equal to?
2 sine plus
2 sine
times.
times cosine. So 2 sine cosine. Now, technically, we've done what they wanted. We've written it so that there's only sines and cosines. But what could you do with that to simplify it a little bit? Think about if you had something like 2x plus 2xy. Is there anything you could do here from Algebra 1? Yeah, you could factor out the GCF, which in this case would be 2x. What's the GCF here? 2 cosine. If you factor it out of the first term, what's left? 1. How about the second term? Sine. I'm not saying it's better or worse to factor out the GCF. I guess it depends on the problem. But that is something you can do. But technically, we answered the question in the step above it. Okay. Any questions on that? Okay. Let's see. So this is really our last problem, because the last group of identities, I give them to you, but we don't do anything with them. Again, so you have them in your notes. Okay, let's try this one because we got about 20 minutes and see. And if I have time, I'll give you the last group to copy down. If not, I'll just put them in the video. And if we need to spend half the class tomorrow on the homework, we can, because we have plenty of time. All right. So, this problem does ask us to solve for the roots. So it's like you're filling in 0 right there. I'm not going to actually go through and finish solving it. I just want to get it to a certain point. Because solving equations is really the next section. Okay? I just want to use the stuff we learned today to get it ready to solve. You notice they say up to quadratic equation. So you'll see what happens. Okay, let's start with sine 2x. That's the easy one. How can you rewrite sine 2x? 2 sine cosine. Now, that's a triple angle. 3x. It's not if it was cosine 2x, all I would have to do is plug in one of those formulas. But it's not. The higher that this number gets from 2, the worse the problem gets. 3 isn't too bad. But if you had like a 5 or a 6, it starts to get really bad. But you can still do it using the same idea I'm about to show you. How could you think of 3x as a calculation of 2 things you added together? 2x and x. Now, that's a cosine sum. Okay? So we're going to use the cosine sum on that, and when we're done, it's going to get a lot bigger. Because remember, cosine sum, it takes one thing, it turns it into 4. But some stuff is going to cancel out here, right? Eventually, not right away. So let's leave the 2 sine cosine right where it is, plus, all right, with a cosine, when we rewrite it, is it a plus or a minus? It's a minus, it's the opposite. Are the cosines and sines grouped or mixed? They're grouped. So it's cosine, cosine, minus sine, sine. 2xx, 2xx. Just fill them in. 2x, x, 2x, x. Okay. Any questions up to that step? Okay, now the 2 is okay, the sine is okay, the cosine is okay, that cosine is okay, that sine is okay. Most of the things here are okay. The 2 things that are not, this and that. They're not okay because they have 2's in front of the x's. So, the nice thing now is though we don't have any 3's left. Once you use the sum or difference identity, now you're down at just 2's left. So if you started with something like a 7, you'd have to write it at, I guess you could do like 2x and 5x, and then do a sum or difference formula, and then you'd have to do it again and again until you keep getting down to just x's. But anytime you can write it as a 2x and something else, the 2x ones will be easy to do because you have formulas for them. We're not going to deal with ones that are any higher than 3. All right, so cosine 2x. Let's write that. This is the part that's a little tricky, but I'm going to write it like that. 1 minus 2 sine squared x. Oh, you'll see why I picked that one in a second. All right, so we've got 2 sine cosine plus 1 minus 2 sine squared x. I put the part I underlined in parentheses so you know what I changed. And what's the other reason that I put this in parentheses? If I take the parentheses out, it would be a different problem. Yeah.
Yeah, so because when you multiply, you want to distribute it to the one end.
Yeah. That's a distributive. Which, when we do distributive, you're going to see some stuff start to cancel out. All right, the sine 2x, luckily we only have one version of the formula. 2 sine cosine. 2 sine cosine times sine. Now, as we're going through the problem, we've hit the worst that it's pretty much going to get. All right. From here, we're going to hope now that stuff starts to cancel out. But any questions on what I substituted in for cosine 2x or sine 2x? Okay, so let's don't really want to rewrite all of this just to do one thing, but I'm going to. So I'm going to just distribute the cosine out. If I was doing this, I probably would have just done it in the last step. Because the more times you keep rewriting it, the more likely you're going to copy something wrong. So 2 sine cosine minus. Now, I'm looking at this, and I'm looking at that. And I'm kind of looking at them, and they're very similar once you distribute. The order in this one is sine and then cosine. So I'm going to do this one in the same order and see what happens. So I'm going to have minus 2 sine squared x cosine x. I just did that. Minus 2 sine squared cosine. Look what you're going to have here when you multiply this out. Minus 2 sine squared cosine. Those are going to be like terms. It'd be nice if it was a plus 2, then it would cancel, but not quite. Plus cosine x minus 2 sine squared cosine x. Now, look at all of those terms. Remember, terms are separated by plus and minus signs. Term, 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 term. I'm going to do it a little different than the way the book does it. What do all of those terms have in common? They all have a cosine. Okay? Let's pull a cosine out of all of them, and then it's going to make that start to look simpler. I know I have some like terms I haven't combined yet. The second and the fourth brackets. I could write that as minus 4 sine squared cosine x. I'm not. I just didn't want to do it at the same time. Okay. What's left in the first term if you factor out a cosine? 2 sine x. What about the second bracket? 2 sine squared x. The third, plus 1. And the fourth, minus 2 sine squared x again. Okay. Now I want to combine like terms. Minus 2 sine squared x minus 2 sine squared x. How much is that? Minus 4 sine squared x plus 2 sine x plus 1. Now, the directions I wrote said up to the quadratic equation. I want you to look at what's inside the parentheses there. It's basically this. Negative 4 something squared plus 2 times something plus a constant. That's a quadratic. That's a quadratic. Okay? Like if I were to fill in x and make the constant like a 5, that's negative 4x squared plus 2x plus 5. So anytime that you have something that looks like that, that is a quadratic equation to solve. Specifically, a is negative 4, b is 2, c is 1. And you use the exact same quadratic formula to do it. So I'm just going to write that off to the side. A is negative 4, b is 2, c is 1. I'm not going to do it. Now, when you have a regular quadratic equation, 3x squared plus 2x minus 5. What are you solving for in that equation? What are you trying to find? Well, you're solving for x. You are always solving for the thing that is right there. It's the thing that's in the middle. So, in this formula, you are solving for what's right there. Look at our formula. What's in the spot that I'm pointing to? Sine x. Not x, but sine x. So when you do quadratic formula, in this case you'd get x equals usually something plus or minus something over something. That's usually what the quadratic formula answer looks like. And there's usually a square root here. Well, when we solve this one, it's going to look like that. So you're not solving for x in the formula we're going to look at. You're solving for sine x. And how do you get rid of sine? Inverse sine. So when we solve one like that, it's going to be the inverse sine. You still do the quadratic formula just like you normally would, but you have to take the inverse sine at the very end. Okay? That part I'm going to talk more about tomorrow. Okay? But as far as a trig equation with a 3 in it, that's pretty tough. Right? It takes a lot of practice to get good at that. Most of the ones we do tomorrow, in fact I think all of them, the highest number I'm going to give you is a 2. Right? Because it takes too long to do it with a 3. Okay, but I might give you one of those to practice just by itself tonight that you don't have to solve or do anything with. Alright, so I think what I'm going to do is I'm just going to put that page in the video. You don't have to copy them down right now. In fact, I won't even give you homework on these 3. But those are called half-angle formulas. We don't use them that much. If you take calculus next year, you might. Depends.
Yeah.
So it's good to have them with all the other ones in your notes. But I'm not going to give you any homework with these problems. Okay, so homework tonight, it's on 417. Careful on question 31, it has multiple parts. I just want you to do part A. Okay, we can take a look at that tomorrow. I mean, even if we needed the whole class tomorrow just to go over homework, we could do that. If not, then we'll start the next section and then we'll probably end up with a review day on Thursday.